introduction to weird but not weird. And the reason that we came up with that topic has to do with some of the things that we...
Hey, well, thank you. Thank you so much. It's good to be here. It's good that you have me as a part of this show because I have a reputation for being a bit weird from time to time and not weird at other times. So I'm going to be right at home.
I can understand and identify with the weird.
Yeah, you saw my recent ad, probably.
That would be wonderful. Oh, welcome Christian Luca to the show.
Well, thank you for having me, Dr. Jones. I really feel very much at home with a title of a show called Weird But Not Weird. It's fantastic. I feel like that my whole life, so thank you for having me.
Well, thank you. That sounds good. What I'd like to do tonight is to take it real slow. And if we have people in the audience who have questions or comments, I want them to, feel at liberty actually to make some comments. And we just had a major light blowout, and so simply because we have so many sick and so forth. And so be patient with us tonight as we get started in a very slow manner. But I wanted to make a statement tonight. What if we could take our Bibles for a moment and say, wow, I'm willing to take theism off the table. In other words, the assumption that there is a God, the assumption that there is no God. Is it possible in this conversation or in this show that we can take those assumptions off of the table and actually put them on the shelf for a while? In doing so, I think that we might be able to see something about the examples that we will give tonight, that is in some of the experiments and the modeling that we want to get into, because we want to talk about something along the lines of not the Bible, but we want to delve into or jump into Dr. David Albert's book. It's called Quantum Mechanics and Experience. Now, this gentleman is an awesome theoretical physicist. He has worked in the Department of Physics, and he also has worked in the Department of Philosophy, because in a sense, sometimes what these people are doing, it makes sense in both of those worlds, if you will. And so currently he's working in the Department of Philosophy, and he has written a book that is extremely powerful, and it's actually helping us to understand, philosophically so, possibly a better system of logic. And so, for lack of a better term, I could call it quantum logic as opposed to classical logic. All of us have somewhat a good grasp of what classical logic is all about, but some things are happening in the context of the quantum world which actually challenge those particular notions. And so one thing that we need to understand in talking about this, that is from a philosophical context, we have to realize that there are actually two meta-languages going on when talking about quantum physics and quantum logic, in that we're talking about wave mechanics, and then we are also talking about matrix mechanics. And so some of the terminology gets well over our heads. I'm not a physicist, I don't claim to be, but what I want to do, and my heart's desire here, is to simply parrot, if you will, put out what others are stating concerning such a wonderful science, such wonderful experiments. I want people to grasp what's going on in a world that's really changing the dynamics of everything. In fact, today people are calling biology quantum biology, simply because some of the experiments that we will discuss tonight have a lot to do with bacteria, all kinds of things. Every object that we're familiar with. In other words, could be put to these same tests with the same kind of results. And so with that said, I would like for Christian Luca, if you would, since this is your background, it's not mine, do you have some?
Coming from the perspective of philosophy, I would say more so than physics, and even though my background is in chemistry and in physics, and the basics of what Professor Albert discusses with regard to the hardness and color boxes experiments that he goes into, and really, you know, this is a learning experience. It's a steep learning curve, I would say. So,
Yes.
yeah, by you going slow for everyone's benefit, I think that's good, because this is important stuff, and I hope that people would understand to the best of their ability what's going on, truly understand, and hopefully people will have questions to ask, and I'd be more than happy to answer them, either from the comment section on YouTube or from the audience, as best as I can with the knowledge that I have currently. So I look for challenges from people. I hopefully people will be flocking to ask a lot of questions. But it is a steep learning curve, and we have to be patient with ourselves first of all, and with everyone else, I would say.
I so agree. Now let me state up front, tonight what we're going to do, we are going to put this in simple terms, because that's what I need here. I need something that I can wrap my mind around. And so when we talk about a color box, when we talk about a hardness box in the idea of quantum physics, you know, what they're talking about is, you know, they're talking about these angular, let's call it angular momentum and spin, and this up and down, and this binary, set process, or looking at things, something in a simple manner. And so I would like to start, but before I do, Bob, what are your...
Technology I've used for other purposes has been that of, I remember as a young guy taking judo, and how one of the guys who came into our class was a strong, larger guy who didn't seem to really be learning judo because he was so strong. He could push people around and do what he needed to just because he had the strength. But as the rest of us were learning judo, learning, leverage centers, and learning how to keep our balance, and learning how to actually do the techniques, we were learning judo, and it was getting more difficult for him. Our brains are designed, as it were, to deal with certain synthetic concepts. I mean, our
Right.
brain seems to deal well with ideas like planes, like ideas of true or false. But our brains also have a wide variety of rubrics for solving all kinds of different problems. And we're really relying on something we find easy to comprehend, instead of really recognizing all the innate ways our brain solves problems. Some of them, when we try to understand how is it that the eye actually perceives an object, recognizes it, and the brain sees it and knows what it is, when you stop to think about all the things the brain has to do to be able to isolate and figure out what it's looking at, it gets weird, and it's not using what we might think of as a straightforward deduction or logic, and it's something that we do so well all the time. We never even stop to think about how it happens, and when we try to stop to think about how it happens, it's almost unfathomable. So it shows me that even innately, we have something going on inside of our brains that is asking us to use something other than the logic that is comfortable for us.
which I'm so against, but it may be what we're relegated to. So I'm trying to tie up a little bit of time, so Daryl, talk to me.
Well, I threw the first weird thing in. Now, actually, I've heard a little bit about what you're going to discuss, and it kind of have a...
We're going to put a C in here for color, and we're going to say that we have this endpoint. Is that me making all that noise? Hopefully not. But we have this color box, and this color box has two options. We have an out, which would be a white, and then we have an out, which would be also a black. And so if we took, just for the sake of making this extremely simple, if we took electrons, randomly speaking, and we took these electrons and we just, let's say 100 randomly selected or gathered electrons, and we threw them into this color box, the result would be 50% would be white and 50% would be black. And the same thing is true with what we call a hardness box. I can draw a hardness box, and I can say we have the N, and then we have this hardness box, which would indicate whether these electrons are soft or hard. And the results would come out being 50% of these would be hard, and 50% of them would be soft. And so it doesn't matter how many times that you do this experiment over and over and over again. You can do this just over and over again, and you're going to have the same results. In other words, take 1,000 or just take 10. You're going to get the same results, 50-50. And this is important to understand at first, that is, in understanding what Dr. Alford is trying to present. And so I want to move on, since we don't have as much time tonight as we had. If you guys have a comment, please make a comment.
Sure.
Okay, now the key property here is that it doesn't matter how many times that you do this. And I wish people in theology would practice, doing experiments like this, Wow, we can repeat this and repeat this and repeat this and come out with the same results. That would be wonderful. And so this is the thing that we need to keep between the left and the right ear. The key property here is they are repeatable and they have the same results. Now,
which can be characterized as reproducible.
Exactly. So let's move to something a little bit more than just one color box. For instance, if we take, I'm going to look at my notes because I'm simply trying to present not what I understand, that is, in doing the experiment, or not what I understand to be true concerning physics. It's what theoretical physicists understand to be true. And I want to make that clear, because none of us here are claiming that we have the ability to do these things. We are simply students, namely, of people who are great in this discipline. And so we want to go slow. Thing that I would like to do is we have an out, which is white, another out, which is black. Now, one thing that we can do is we can go from this, and please understand, remember the results. If we go into a color box, it doesn't matter what number we put. You take and go into this color box with these electrons. Let's just say we want to analyze, if you will, the white electrons. And we take this, or these actually, into another color box. And if we have an out point here, which would be white, and another out point here, which would be black, the results would be we have 100% white and 0% black. Now, so far, this makes sense to all of us who have, somewhat of an understanding of classical logic. But in a few minutes, a lot of this is going to change. So let's just, we can go into the hardness box and out of the hardness box, or when these electrons get into the hardness box, they will come out 50-50 as we discussed before. We will have 50% of them coming out hard, 50% of them coming out soft. If we continue to go over to another hardness box out of the soft side, out of this soft aperture, we have 3 apertures here. We have 1 going in, we have 2 coming out. If we come out of the soft aperture into another aperture that is in this hardness box, and we come out, that is soft, and then we come out hard. We're going to come out with the results like we did in this example or this experiment with color boxes. In other words, in this case, if you go in to a hardness box, you will have soft, that is the electrons coming out soft will be going into this hardness box. They will come out 100% soft and 0% hard. Now I'm going to take my time because I don't want to rush through this, because any time that this is the first time that you have ever seen something like this, it may, twist your mind a bit or get you to think differently about, things. Right now it seems, wow, this is just making sense to me, and classical logic really works for me. I'm not saying we need to do away with classical logic at all. I'm just simply saying that when we go through all of these things, we might find a little bit of pushing back on our understanding in the classic world. So, did you have a comment to make at this point, Christian?
No. Well, the only thing perhaps that may be important for the audience to understand with these 2 parameters we're talking about, color and hardness, is that these properties of color and hardness are not correlated properties, meaning...
Okay, okay, before you get into that's the next place or next point that I was going to make. Yes.
Sorry, I apologize. And I thought that's important to mention, and I got ahead of myself, so I apologize.
Okay, now someone is asking the question, what are we putting into the boxes? We are actually putting electrons, but this is something that is true if you put photons in this. As Dr. Adams stated, he said you can take a buckyball and put through these devices, and the results will be the same. This is the dynamic issue of what's happening here, and so I want to take this in baby steps, if you will. And so what we're going to talk about, or a question would be, are color and hardness, can they be related or possibly correlated? And let's look at the 2 things on the board. And let's see, if we take some random, we're taking random electrons, and we take white and you go into a hardness box. Now, this is interesting, quite interesting to me. You have hardness and you have soft. Now, the results that you're going to find is that when you come out of the color box, and 50% of the electrons will be called black. And so we have 50-50. Now we're only looking at our white electrons. Let's just take the white ones and put the white ones in the hardness box. And the results are going to be they will come out like this. 50% will come out to be soft. That is, of the white ones, and 50% of them will come out to be hard. Now, Christian brought up that these are not related, and we will demonstrate why that's so. So let's take this and look at it like this. Let's put another in. draw a box. In this case, we're going to start with our hardness box. And we are going to draw an arrow here, come out, here's a soft, and we can go across here into, namely, a color box. Now the color box has white, that would be the out white aperture and the black aperture. And the results would be that, randomly speaking, a collection of electrons going into the hardness box, 50% of them would come out of the hardness box hard, 50% of them would come out soft. Now, out of this 50%, if we take these directly into the color box, 50% of these would come out white, and 50% of these would come out black. Did you have a comment, Christian?
My only comment here, the experimental results are correct, indeed, as I understand them. The only thing is, I would say at the beginning, when you mentioned that you have a random sampling of electrons,
Right.
I would say, actually, from what I understood, actually, if you want to demonstrate that there's no relationship or no correlation between the color property and the hardness property of electrons, actually, you would send in, let's say, all hard electrons into the color box, and you would get 50% black, as you said, and 50% white, as you said. So, but I think the initial point, entry point, the input, I don't know that it would be random necessarily, but actually it would be, you actually purposefully set up all hard, or let's say all soft electrons. It could be either one, all hard or all soft, and you introduce them into the color box, or you started off with the, I'm sorry, you started off with the hardness box on the bottom. Okay, but on the top. So what I'm saying is, I don't know that it's accurate to say that you start off with a random sampling of electrons, but with an actual sample of electrons that are either all hard, right? All hard electrons, or all soft, and you introduce that into a color box, and you get out 50% black and 50% white, as you said, Dr. Jones.
But David, Alfred, is that if you take, randomly speaking, before you go into a hardness box, let's say that I collected 100 electrons and I put it into a hardness box. Is it not true that 50% of them would come out hard and 50% of them would come out soft? Would that be an accurate statement?
That would be an accurate statement, Dr.
Okay.
Jones, yes.
Now, if you took 100% of the soft ones, in other words, the ones that you put into the hardness box, you took all of these and sent them into the color box, they would do what?
Would come out 50% black and 50% white.
Right. That's what I've demonstrated on the board.
Indeed.
Okay. And so I didn't know whether you were saying that you had to have 100% here
Yes.
to set the stage, or whether this was something that we could have an in, namely with random electrons, which I think both of those physicists declare that this is what's happening. Or am I wrong?
Well, I have not watched a lecture recently. I watched about 2 weeks ago with Dr. Adams, but from what I read recently, in order to demonstrate that there is no correlation between hardness and color property, right, you would have to introduce initially, let's say if we're looking at a color box, we would introduce all hard electrons or all soft into a color box, and what we get out would be 50% black and 50% white. Now, if we want to look at the hardness property and its relationship with the color, we would introduce into a hardness box all white electrons or all black. It doesn't matter, really. If you were to introduce all white electrons into a hardness box, what would come out is 50% hard in the up aperture and 50% soft in the horizontal. It doesn't matter which aperture, but 50% hard and 50% soft. What you'll get out of a hardness box will always be 50% hard and 50% soft. Okay, and the same goes with regard to the color box. If we introduce 100% hard electrons, okay, you'll get the result: 50% black and 50% white. Same goes if you were to introduce 100% of the electrons being soft, okay, into the color box. Again, the result will be the same: 50% black and 50% white. So maybe what you're referring to when you said that there's a random distribution, maybe, you know, this is what it's talking about, that it doesn't matter whether it's, you know, hard or soft that you're introducing into the color box, you know, you're still going to get 50% black, 50% white. So, but I just sort of broke it down maybe a little bit more concretely than perhaps what Dr. Adams did, you know, in his lecture.
Okay. Okay.
I think maybe that's what I've been doing, just breaking it down a bit more concretely, you know.
Bob, did you have a point to make?
No, not really. I'm waiting for us to get to the point where we're going to start getting results that we're saying, what? and I understand that that's going to be coming next, because we're going to find that when we start mixing things up a bit, we would think that we're starting to strain some things out, and it turns out that we haven't.
Okay. Now, because that's basically actually that's our next step, because from what I understand, and I'm just going over this in a very simple way, you just take some electrons, throw them into a color box, they will come out 50% black, 50% white. That's what you're saying. Is that true, Christian?
Yes, that is
Okay.
correct.
And so out of the color box, the 50% that come out white, you can take those into a hardness box, and they will also come out 50% soft and 50% hard, correct?
Correct. As
Okay,
well.
and the same
Yep.
thing is true if you start out initially with a hardness box. You can simply take a grouping, namely of electrons, throw them into a hardness box. 50% of them will come out hard, that is, out of the hard aperture, and 50% of them will come out of the soft aperture, correct?
Correct.
And
Yeah.
if you take out of the soft aperture and place only those that came out through the soft into the color box, not black, 50% of them will come out white, correct?
Correct as well.
Okay.
Yeah.
Okay. Now, with that stated, let's move on to our next point. And you guys jump in at any time. We're just talking here tonight. And the thing that I love about this, this isn't based upon guessing. This is based upon people who take the time to build devices, who know what they're doing, and they do experiments all the time. They do the math, they do all of this, and to me, this is a breath of fresh air. People willing to say, wow, let's look at things and let's figure out how things work. And so this is what's happening today. Now, let's think about how hardness and color may be uncorrelated. Let's demonstrate something for a moment. Okay, if I go into a color box, let's use blue. If I take a color box and I go in to the color box, and I'm going to have B for black, W for white, and if I take whatever comes out of the white, and remember in this case it would be 50-50, if I come out of that into a hardness box, I have hardness and softness coming out of my hardness box. If I continue to travel out of my soft box, now please look at what's happening here. If I go into the color box, 50% of them are going to be white. Let me write this down. And 50% of them are going to be black. So I'm only taking the white into the hardness box. When I take these into the hardness box, as we've already demonstrated, 50% of these will come out soft. And out of the hardness box, 50% will come out hard. If I continue, I can go back into a color box, and one would assume that if you are only taking white ones into a hardness box, I want you to listen to this. This is where things start changing, because all of the black electrons have not been placed into another box. We only have white, that is the ones, 50% of them come out soft. Now let's take the soft ones that were considered to be white, and let's take these soft ones which were considered to be white, let's take them into another color box. And so let's put white and soft. White and black, excuse me. Now, I'm going to ask our audience, what do you think the outcome's going to be? Do you think it's going to be, let's make a prediction. Are we going to have B and W, white and black? Are we going to have 50% black and 50% white? Now, I'm going to sit here for a second because I think that our feed is about 10 or 15 seconds ahead of time. I want to see some people actually who are viewing this show writing some of this stuff down. Now,
yeah, and I can assure them it's not going to come out gray.
It's not going to come out gray. That's true.
That's right.
So I'm simply waiting on the feed to see who's predicting what. Okay, now some people would make this kind of prediction. 50% would come out black, 50% would come out white. Now let's go back through this again. You have electrons. They're placed into a color box. 50% of them come out white, 50% come out black. Let's forget about the black ones. We only take the white ones into the hardness box. When we take them into the hardness box, that is the white ones, they come out 50% soft, 50% hard. Now the ones that were white that were thrown into the hardness box, we take the soft ones that were white, that are white, and we place them into a color box. Now the prediction is based upon, we could say classical logic. I'm not confident in that, but we could say that most people would go with 50% black and 50% white. Would you think that that would be a classical conclusion, Bob? Hello, Bob, are you there?
No, I'm losing the connection. I can't, you're disappearing from me. I couldn't hear anything.
Okay, let me go back to this.
I can answer if you'd like.
Okay, the prediction would be, if I said that coming out of the color box, well, let me go back to the beginning here because I really want people to get this point, because if you take electrons, you go into a color box, 50% of them will be white, 50% of them will be black. If you come out, not out of the black, let's leave the black electrons alone. Let's only deal with the white electrons. And let's take these white electrons into the hardness box. the results will be 50% of these white electrons will be soft, 50% of them will be hard. Now let's take the soft ones, and we know that they are white. Let's take the soft ones and take them back into a color box, and let's see what the color box suggests. White, black, what would be the percentage? And so Bob, based upon classical systems of thinking, that is...
I'm going to expect them 100% to be white.
Mm-hmm.
Okay, that would be a classical conclusion?
Yeah.
That's right.
Okay, now most people in classical thinking would say, and I agree with Bob, their prediction would be 100% of them, and I got it wrong a few minutes ago, and so I do apologize, 100% of them would be white, and 0% would be black. And this right here would be the classical conclusion. However, when we do the experiment, and this experiment has been done thousands upon thousands of times, it always comes out not like this, white. And so the prediction comes out quite different. And so this is why I think that the whole system, in other words, in the way that we are making conclusions, needs to be, in a sense, thought out again. In other words, we have been thinking, well, if it's white going in, it has to be white coming out. And so I'd like for you guys to take the ball at this time and talk about this, because I find this to be fascinating.
Yeah, and I'm not enough of a physicist to really to talk about it much. I read this stuff. I find it fascinating. To me, I don't know that we even have a way of determining. Well, it appears to me that the quality of being a white electron is not persistent. And how does it change? When does it change? What causes it to change? How is it possible? I mean, we could put it through a color box, put it through a color box, put it through a color box. It comes out white. But why is it when we're testing for hardness and then test for color, then it is impersistent? That seems strange to me, and we don't know. We don't have a way of determining how that happened, when it happened, or what causes it. Particularly when we know that there's no correlation between hard, soft, and black-white.
Now,
Right.
So I'm lost.
Yeah. The thing is, the hardness box, you could say, sort of disrupts the color property of the electrons, but
Right.
you don't know how to find out how that happens.
Yeah.
There's no
Exactly,
way.
because if I test for color, and then I test for color, and then I test for color, it persists.
Right.
But if I test for color, and then I go for hardness,
Mm-hmm.
and then I test for color, it doesn't persist.
Right.
So why, and we know that the two are not correlated, so why is it that because I tested for, I say, well, forget about color. Let's take a look at, let's just totally forget about color, let's look at hardness.
Mm-hmm.
Having done that, now the color has not persisted.
Yeah.
That's
Yeah. You could say that there's a superposition going on of of hardness. Let's say hard and soft. If you're sending in white electrons or black electrons, and you're testing for hardness, you'll get 50% hard and 50% soft. So you could say, using the language of quantum mechanics, quantum logic, that there's a superposition of hard and soft. right? But as you said, Bob, that there is no correlation between color and hardness, correctly said. And there is no way, it seems, that we can build an experiment to show where that disruption of color is taking place. You know.
Now, one of the things that I found interesting about Dr. Adams' lecture on Dr. Alford's conclusions, namely in his book, is that he brings up this, I would call it a classical first move. Someone would say, oh, okay, I see the results, but surely there must be some additional property of the electron that we just haven't measured yet that determines X, Y, or Z about the outcome. Whether it comes out black or white, there must be an additional property that determines this. I think that most of us would say, you know, there's got to be some kind of explanation that tells us that something is happening within these boxes, something's being tampered with. And that does come up in our minds. Would you agree with that, Christian?
Yes, definitely. In this case, we're looking at the hardness box tampering with the color of the electron because, as you said, Dr. Jones, we're sending in just the white electrons into the hardness box and getting out soft and hard electrons, and then we're just looking at the soft and we're sending them again into a color box and we're getting out 50% white and 50% black. So we can say that there's some tampering going on in the hardness box. And we don't know exactly what's going on, really, in that hardness bucket. There is tampering, yes, but how can we actually go about determining, you know, how that color is being disrupted in the hardness bucket? I think that remains a mystery. I'm sorry for the echo. Yeah.
Let me read this. And I'm taking this from, and I can't remember the gentleman's name who stated this. He said, you can't think of an electron with black or white written on it. They are persistent if you put them through, let's say, let me give an example. If I take a color box here and I have black and white, and I put my endpoint here, 50% of them will come out white. 50% of them will come out black. Everything that comes out white, I can put it into another color box. And here, we're going to find that they will always come out 100% white and 0% black. Now that's a given. But it's like if you put it into the hardness box and you only feed into the hardness box white electrons. If you take the white electrons that are soft and place them into a color box, they come out 50% white, 50% black. That's where everything changes. That is where it gets weird. Would you guys agree with that?
Exactly.
Definitely.
Testing for one causes the other property to, but it doesn't just, it's not like it fails to persist. It fails to persist perfectly.
Yeah.
That's a good point. That's a good point.
The explanation as to, I mean, I'm just curious as to why that it's always an even thing when they split out the bottom. I mean, they're always 50%, never 49, never 35. I mean, it's always even.
Yeah.
Now, if you have just joined us, what we're doing, we're talking about things that that may change our world, our understanding of logic, the way that we understand how to deal with everything around us, because according to Dr. Adams, this just doesn't have to do with electrons. This has to do with, you know, the components within bacteria, to you name it, and all of the objects surrounding you. you can put them into this kind of test and the results will be the same. I stated earlier, you can take a buckyball, throw it into this context, and you're going to have the same results.
It seems as though one of the things that we're recognizing is this. It seems we could call it observing or testing or detecting, that the act of detecting for a particular property seems to allow properties we're not detecting for to be persistent.
Right.
This calls into question empiricism. It makes us say something's happening here, detecting and observing seems to be affecting things, resetting things, as it were. In a sense, that's another way of looking at it. They've been reset to being randomized again at a perfect 50% each. And so we have to ask ourselves, where does this end? Where does it, so that we're not really sure how far we can apply this. I mean, if we were to take actual tennis balls and billiard balls and make sure that they're also two different colors, and we sift them out this way, we always end up with the classical logic.
Mm-hmm. Yeah.
But when we're dealing with objects that are physical particles, well, now this is where we're having the problem.
Well,
yeah. So it makes me wonder, where's the border for this? Where's the edge for this? Where's and what are the implications of this? It's not clear to me.
You know, Dr. Jones, to make this clear to the audience, I think Bob brings an excellent point, and also Daryl earlier with the 50% black and white. Why is it that? If we harken back to our understanding of the conversation we had about the double slit experiment, right? We talked about localization when we're observing the electrons passing through double slits, right? Or the photons, whatever it was that we were observing, which slit they were going through, right? There was a certain pattern that would develop on the photographic plane, okay? Which was distinct, was different from the pattern, the interference pattern that would develop when the observer was not looking, right, on that photographic plate. There seems to be an analogy going on here with the color and hardness boxes. If you were to do an experiment where you put a barrier and you observe, you get 50%, and in this case the barrier is the hardness box, right, Dr. Jones? You put up a hardness box in between the two color boxes, right, that you have on the first row up there. That's sort of the barrier, okay? And you get out the result, 50% white and 50% black. That hardness box is sort of an observer. It's sort of interacting, you see. Sort of like the way people are looking at the two slits with the detector to see where those electrons are passing through. I'm just bringing it back to our conversation we had a couple of weeks ago.
I can see your point, but your suggestion would also make the color box an observer, and so regardless of whether you're going into the color box or the hardness box, you're always having an observer in the context of which you speak, correct?
You could, yes, that is correct. I guess the question where Bob was saying, how far can this implication go? And yeah, I'm not sure.
Now, there's been a lot of time, effort, and money spent on putting together these boxes. And I'm quoting Dr. Adams once again. He said, regardless of how we build these boxes, we have the same results. And so they have been built in various ways. In other words, it's not always true that we have the observation of, namely, of what these these electrons are doing in the box. It's kind of like, wow, we're at a loss. And so these people carrying out the experiments, obviously they know what they're doing. They've done it in so many different ways, but the outcome always comes out the same way. And in
They've
fact,
even taken care of problems of interference. For example, let's just send an electron through the whole spiel once a week.
Right.
One electron once a week. That way, I'm getting a tremendous echo, by the way. When the electron goes through, if you send the next one through a week later, there's not likely to be any interaction between them. So it's not as if they're affecting each other.
but if you send them, let's say through in this case, if we send it through the color box and then into the hardness box and then into another color box, let's say one every month, the outcome would be the same as sending them in every 2 seconds, or
Exactly.
just and the results are always the same. And I find this to be just wow. We've got to rethink things. In fact, some people are saying or suggesting, what does this suggest about determinism that is from Newton? And when I think back on that, I go, wow, what a pushback in a sense. I mean, there are so many things that we need to think about in the context of determinism that was suggested by Newton in his context.
We have this concept from probability that can be something similar. If I toss a quarter up in the air, the probability that it's going to come up heads is 50%. If I toss a quarter up in the air and I happen to get 3 tails in a row, now when I toss the quarter up in the air, what's the probability I'm going to get another tails? It's still 50%. It seems like every time I look at a single event and its single probability, its probability is always irrelevant in terms of previous events that have already occurred or might yet occur. And so the probability doesn't change unless I'm going to say, what's the probability that I can actually get 4 tails in a row? Now that's a different probability. But if I get 4 tails in a row and I'm going to toss the coin up again, it's still 50% probability that I might get a tails. And then if I get 10 tails in a row and I'm going to toss a coin up into the air, it's still a 50% probability that I'm going to end up getting a tails. This is the way probability works. And there's something going on here that is somewhat similar that seems to create a situation where the persistence of, or the constancy of something is altering things that kind of resets them to random, to chaos. And what this does, particularly this is happening at the atomic level, and you say that the question of determinism. In fact, determinism is based upon a belief that the whole solar system is operating right down to the very foundation of its particles in a very mechanical, deterministic manner, and evidently it isn't. So where does this fall apart, if at all?
If I may interject, Dr. Jones, because Bob mentioned random and chaotic, and there is a distinction from what I understand mathematically. I'm not a mathematician, but I have to bring this in because we're talking about stuff we're doing in nature, right? We're talking about experiments, right? And so from an empirical point of view, as far as we know, there isn't any phenomenon that is random as such. There are many phenomena that are chaotic. An example of a chaotic system is weather. And why is it chaotic? Because if no one will ever know the initial conditions of a front, of a cold front or a warm front. But if we were to know the initial conditions, right, and if those initial conditions were tweaked a little bit, right, over time the evolution of the dynamical system would diverge in different directions based on the changing the initial conditions. That's what a chaotic system is. So just to bring that in. That may be tangential to the color and hardness boxes, but
Right.
just wanted to bring that up.
And of course, another aspect of the difference between random and chaotic is random indicates a pattern that we're looking at of predictability. And chaotic is a admission that there are so many factors involved in what's going on here that we don't know what is causing the differences to be occurring, and in a sense it can create a pattern that appears to be mathematically random, but it's really chaotic.
Right.
Yeah.
Right. Precisely.
But by the way, I couldn't hear too much of it. Couldn't hear what Christian Luca was saying because it was such an infinite echo coming back at me. Dr. Jones, if you could maybe, what was it that Christian Luca said? You're not echoing to me, but
I could not hear Christian adequately. In fact, I'm questioning whether I want to go much further with writing a lot of this down, simply because I want to look at this and examine this, because where this leads us to, and I will cut to the chase, I want to read this. It brings us to the conclusion that maybe I just need to save it, because if I spilled my guts right now, it's like ruining a good joke, and I don't want to do that. But you know, this is a fascinating study. These experiments have been going on for a long, long time, and I will say that no one has found an additional property that would change that outcome, or that is
explains it.
yeah. And if they did, you know, they would be famous. They would, you know, get the Nobel Prize and all of that.
Yeah.
But you know,
But I think we achieved our goal, don't you?
Right.
I mean, we wanted to show something that was weird, and
But-
here we got it. It's weird.
but I would suggest some reading for some of you guys who are wanting to stay with us, because we're going to be dealing with this for a few weeks. Please pick up the book by David Albert, Quantum Mechanics and Experience. And also, I would, encourage you to read Bell's Inequality, especially at the point that we are now, simply because it really, really would help to fill in some of the gaps that I'm certainly not capable of. But it doesn't matter. For instance, it doesn't matter how many times we go back and try to observe, look at, examine, and do this test over and over again. We still haven't been able to find anything additional that's going on that would give us reasons why the conclusion would be 50% of these in this particular color box would come out black and 50% of them would come out white. This is just something that happens, and this is strange. I'm not saying that there's not an answer, but this certainly does get us to thinking in a different manner. Okay, Christian, did you have anything else to add? Because I want to close the show earlier this evening, simply because we are having technical difficulties, and I don't want our audience to suffer. But we are getting the ball rolling here, and next week when we come back and continue this, we're talking about this introduction to weird, but not weird. And so I'm hoping that we can get a lot of people involved in this discussion, because this isn't a time of us trying to teach you. This is a time of conversation. I encourage everyone, start picking up some books. Don't pick up, just the Bible or your favorite science book. Pick up all kinds of books that are written by people who really know what they're talking about. And I really emphasize really know what they're talking about. Try to choose people who have a methodology. In other words, the sad thing happening today in theology, and that has happened for so many years in theology, it's that people are saying anything and everything without having any kind of method or practice to it that makes sense. But we have some awesome people in the context of quantum physics, and now quantum biology, and the quantum level is growing and growing and growing, and we are dealing with the basics of the quantum level tonight. And It should be fascinating to everyone because this really is where things are going. This is very, very exciting. In fact, next week, what I'd like to do is I'd like to finish up on the color boxes, or the color box and the hardness box, and go into the double slit. Because I think that David Wallace, this guy he's quite the genius. He really has a way of putting that together in a manner in which I think that all of us can see. And then I think that when we are contemplating Schrodinger, that is his writing concerning, or his thought experiment concerning the cat in the box, I think that it will bring some understanding to all of us concerning that. And so, did you guys have anything else to add to this program? If not, we're going to close early.
Not really. I think we've established the weirdness what we're talking about. The book, by the way, is like about a $25 book, but you can actually buy them used off of Amazon too.
Right, and you can get a Kindle, which is I think it's about what, $14? Is that?
Mm-hmm.
Can you see that on screen, Bob? It's about $14, but it's an excellent book for someone who wants to rethink logic. I mean, David Albert is an awesome individual. In fact, he has a lot of videos on YouTube. He's really someone. I think he is as good as Sean Carroll. Sean Carroll is awesome. If you want a good debate to listen to Sean Carroll debating William Lane Craig. William Lane Craig had his butt spanked in that debate. This guy, he's so kind, he's so nice. But he knows his stuff. I mean, he's just really, really good. So pick up some of these, books like from David Albert, Quantum Mechanics and Experience, and find some of these other guys and do some reading before next week. And we want to come back together and just investigate this. We want to talk about where should we be today, logically speaking. Should we hold on to just the thoughts of Plato or Aristotle, or should we continue to move forward, namely with our logic system? And so many people are out there challenging all of us, and so I'm enjoying the ride, and I hope you are as well. Final thoughts. Daryl, I haven't heard from you much tonight. What are your thoughts on this?
Well, and speaking of what you just talked about, maybe it's time for us all to take another step. That would be good. A step forward.
That sounds good. Christian Luca, what are your final thoughts?
Well, this evening was a great evening to establish something that everyone should understand with regard to quantum logic, the weirdness of it. So we've accomplished that, no doubt. And I'm encouraged that we'll learn a lot more. This is just the beginning. It's just scratching the surface, really. I thank you for your suggestion for that book, Quantum Mechanics and Experience by David Albert. I have not read it, but I'm very much interested in looking at it. So thank you for that. And, hopefully we can go into the hardness and color boxes a bit more next week. Perhaps talking about the two-path device of the color and hardness boxes, because that'll help build upon tonight's conversation even further, and perhaps add to more of the weirdness, but also lead to the other part, being not weird too. As we begin to understand more, we'll start to really see things as not being weird. But it takes time. So I'm patient. Everyone else is patient too.
Now, there are various people watching us tonight, and I really thank you for all the comments. And let me simply state that the reason that I didn't want to get into answering some of the questions that were very, very good. Let me read one. what is the electron exposed to in transit between the boxes. One of the things that, if we would have had time tonight, we would get into, we were getting ready to go into a world in which we would actually block one path, and we can see what's happening there. And so this brings up a lot of things that would supply possibilities for you to think about. But I did not want to answer that
In the book,
tonight
he
simply
goes into
because
that, by the way. He goes into the book to eliminate some of the possibilities.
exactly. But I didn't want to go into that tonight without putting it on the marker board first, because I think the marker board is going to serve as an advantage in this conversation. And please, you guys keep correcting me. I'm trying to get these things right. It's
You've been wonderful, Dr. Jones, really.
well, thank you. I'm really Joe's with us. They have encouraged us to get the conversation started, just to talk and just get conversations going. And please understand this. My heart is, I hope that we can simply put away the assumption of there is a God and the assumption of there is no God. I hope that we can put that to the side for a while and actually start talking about methodology, talking about things in science, talking about the arts, talking about whether God exists or not. That is useful, but it doesn't need to be a conversation in which we become obsessed with. I mean, so many people are obsessed with that conversation. I don't think they can see anything because of the obsession and the compulsion.
Yeah.
And so I'm wanting to put that on the shelf, and I hope that I can do people a service by, suggesting put God on the shelf, if you will, whether you believe in Him or not. If you don't believe in Him, put that on the shelf for a while. If you believe in God, put that on the shelf for a while. I mean, it's not going to hurt Him, and if He doesn't exist, it's fine. And let's not make everything about the great debate. There's so much more in life to explore. These theoretical physicists, they are coming to some fantastic conclusions, and what really makes all of this crazy, I'm not talking about in a good way, it's when theists start saying, oh wow, there's proof of God. Don't try to shove God into every conversation. Damn, quit that. That's nonsense. Look at quantum physics for what it is. Enjoy what man is discovering, what man is doing, what man is authoring. Put God on the shelf for a while.
Yeah.
Can I give you two?
Yes.
Can I give you two applications of what we're talking about here?
Mm-hmm.
Let's say, what if we were to understand what Newton said about gravity? And I mean, not believe it, not doubt it, just understand it.
Mm-hmm.
It was very useful to use for a while. Finally, Einstein comes along, and he shows us that Newton was not quite correct. Well, what does that mean? What purpose does it serve to have believed in Newton rather than just to understand him? And then what if Einstein gets proven to be not quite correct? And there's some things about what he's shown us that we did discover. You got to tweak that a little bit. There's a sense here in which we're too gung-ho on trying to think we know now. We now know. We don't need to know. When we have a good theory, all we know is that we have a good theory that fits in very well with the evidence that we're looking at. That's good enough to just understand that it does. We don't need to be trying to turn it into some sort of a tug-of-war or some sort of actual, I would say, egotistical certainty that we seem to want to have. I think we'd actually, many times evolutionists will be disappointed that they don't seem to be able to teach evolution to creationists. And I think that part of the problem there is oftentimes you're trying to get them to believe in it. Don't. Just try to get them to understand it. You'll make so much more progress. Expect them to understand it. And to me, sometimes the illumination of understanding something that you don't necessarily even resolve it frees you up to even go into greater depth.
I
Yeah.
like what one of our commenters had to say. What would happen if we ran the Trinity through the color box?
Oh my.
That's funny. I don't care who you are. That's funny. One of the things that I love about
You
theoretical
get a
physics.
communion wafer.
Yeah. For the most part, most theoretical physicists in the world were asked which position did they hold to. Some people were with what's called the Copenhagen, and some people were with the Everett version and various other versions. And one of the things that I began to see several years ago was these people are multi-axial. They're not all standing, in a sense, on the same axis. And so enjoy the fact that people are looking at things differently. If you will listen to these professors, these guys are saying, at the end of this course, you're going to realize we really don't know anything about anything. And it's wonderful. And they're just trying to get people to let go of the notion of certainty. They're simply trying to encourage people, let's take another breath of fresh air. This is awesome what we are looking at. For instance, when it comes to the Higgs field, wow. Jump into that with both feet, because what that is telling us is
Can I offer
mind-boggling.
one more comment here?
Certainly.
Something I find a little disappointing is that the things we've been talking about tonight are things that physicists have been talking about for over 20 years. And yet, the general population has not been looking at some of these issues that bring us serious questions. And part of me has to wonder why. Why is that? I think what is this mechanics and experience? Was that written in 1994?
I can't remember the date, but it's not recent. It's
Yeah.
These tests have been going on for a long
Exactly.
time. We're talking about not just one or two tests, but we're talking about lots and lots of people engaged in making these
and
devices.
for a long time. And so
Yes.
why is it we have not been benefiting from something that's been established for that long of a time?
Yeah.
I find that to be somewhat disappointing.
It
Makes me feel like
is.
our educational system is not trying to keep par.
Bob, the way I would explain that is sort of an analogy. Usually the mathematicians come up with some abstract piece of math. Like, for example, Fourier came up with his wave functions about sines and cosines making up a curve, essentially. And then after 100 years or so, the physicists and then the chemists start to realize, oh, this is useful for our endeavors, right?
Right.
So, they follow, the physicists and the chemists and then eventually the biologists. And I think that takes time to filter in, to percolate into the rest of society. I think the social sciences, the humanities have to come in touch with this stuff, and it takes them a while. I understand your frustration, don't get me wrong,
Yeah.
Bob, I really do. But it takes some time, and even within the sciences, usually the mathematicians are the ones who are off in their own mathematical world that's magical, and they don't care about this physical universe, and they're coming up with neat stuff, and then here comes this physicist 50, 100 years later and says, oh, by darn gosh, I really think I can use this here in my experiment,
I teach sound engineering, and one of the things that I'm amazed at is when I'm dealing with students who are very fascinated with sound and interested in dealing with sound engineering, that when I'm trying to explain to them some of the scientific principles behind it all, they're hearing this for the first time, and yet it was German technology even before World War II that was exploring so much of what was going on that these physicists had dealt with in terms of, these kids have not yet discovered, even though they've been interested in music, interested in sound, interested in this, and that, they don't know that sound is actually periodic variations of atmospheric pressure. They don't realize that a microphone finds a way of converting those periodic variations of atmospheric pressure into periodic variations of voltage. And how a tape deck, found a way of converting, transducing the periodic variations of voltage into periodic variations of magnetic field, and how all of this works, and it all operates according to the laws of physics. None of it is magic, and people had to figure out how to make all of these things work step by step, and they've been doing it for years, and yet we have people who are fascinated with sound. They want to take sound engineering, and they've never heard of this stuff before. Now, I'll tell you, I've been involved in sound for a long time. I've always loved this stuff, but to me, I always want to know what's going on underneath the hood, But I suppose there's a part of me that kind of grieves the fact that we don't have students today who are just hungry to say, I want to get down to the bottom of this. I want to find out what's really going on underneath the hood. And I just wish we could encourage more of that.
We do have some comments that I would like to address. Someone said, if the physicists can't understand what's going on, where does that leave the layman? Let me see if I can make this point. I've listened to so many over the last 6 months to the last 2 years. And I will say this, when you hear one of these physicists state things are just weird and goofy, sometimes what they're suggesting is you are going to think that it's weird and goofy. And yes, to us it seems a bit weird and goofy simply because we've held on to a classical sense of thinking for too long. But now they think, and I'm talking about theoretical physicists, not me, they think that the classical way of looking at things would be considered to be weird and spooky. And so it's, a lot of things are stated in tongue-in-cheek in that kind of context. And please understand, what we are going to do here at the Cult of Honesty, we are not going to make things too difficult. In fact, we are going to do something every week to simply do some footage to put things together. In fact, we have we're trying to order the products to put this double slit experiment together, so we can put some things together with, namely, our cameras, and see if we can come up with some better visuals of what Dr. Young was looking at years ago and how much progress that we've made, and we can participate in this kind of context to see what other people are looking at and make it very, very simple, because in a practical way this will help every one of us, because it helps us in the context of thinking. It will stimulate us. My wife and I, from time to time, we sit down and we watch a lot of these professors on our television simply because it's better than going to the movies. These guys are exciting speakers talking about things that are just awesome. You want to be in awe, pull some things up on YouTube. You can order things through Amazon, other places. Just so many lectures out there. There are courses that you can take in all of our universities around. Wow, just great places to go. But I think we're going to make some progress, and so this is the place where we are attempting to move forward. We're taking baby steps now, and I think this is what the theoretical physicists are actually stating. We thought we knew a lot, but in reality we're simply taking baby steps. And so this is going to be an interesting conversation, and hopefully a better conversation as we continue to learn together. That's what it's going to take. So this is going to be it.
I'm just looking to understand the universe a little bit better. That's all.
Yeah.
That's what I do as well. So.
Hey, thank you guys for your time, and we will be back next week at this time. And so you guys be patient with us, and let's keep coming together. Have fun.